Here in part 4, we're going to talk about the Electron Tower. Oxidation and reduction reactions describe the release of energy between electron donors and electron acceptors. So we have compounds that are reduced, they give up their electrons and become oxidized. And in the other half of this reaction, we have oxidized compounds that pick up those electrons and get reduced along the way. There's a good summary discussing electron towers at this Oregon State website. I encourage you to take the time to go explore that website. In the electron tower, the concept is that you have donating electrons, compounds on one side, and you have receiving oxidant compounds on the other side. So glucose gives up its electrons and is converted to carbon dioxide. So let's take a look at how this works, because this is the basic mechanism by which plants and animals, microbes, archaea, bacteria, all conduct reactions which result in the generation of energy that's used to synthesize ATP. This electron tower can actually be seen in nature, which is part of this week's exercise, in a Winogradsky column, in which we have different groups from the top to the bottom of the mud. And the product of one, the waste product, you might view it, of one, becomes the substrate of the next as we move down this electron tower, getting deeper into the soil. The larger the drop in the electron tower, the more the energy which is being transferred. So the biggest drop in this electron tower is the conversion of glucose to CO2 interacting with diatomic oxygen. I like to use a song to help me remember how this works. So I'm going to play a children's song to get you into the mood.
You put your right foot in, you put your right foot out, you put your right foot in, and you shake it all about. You do the hokey pokey and you turn yourself around. That's what it's all about. You put your left foot in, you put your left foot out, you put your left foot in, and you shake it all about. You do the hokey pokey and you turn yourself around. That's what it's all about.
Okay, catchy, isn't it? So let's go back and look. We're going to talk about glucose interacting with diatomic oxygen. And in that reaction, you put the left side in and take its right side out. And on the other side, you put the right side in and take its left side out. You want to make reaction, so you shake it all about. Dot, 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 dot. Now that's no hokey pokey, as anyone can see. We use this electron tower to give a cell its energy. I hope you like this tool because all of life needs ATP. Dot, 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 dot. Okay, look for this to be a hit in iTunes, coming soon. So once again, we take the left side and the right side is on the other side of the reaction. For those that are receiving, we have the right side on the left side, and then the left side is out. So what we're looking at once again is glucose plus oxygen results in CO2 plus water. Now, in this big drop here, we get the most energy exchange of all the possible exchanges that are shown here. This is an aerobic reaction, but we can also have glucose interacting on anaerobic reactions. So we can have glucose interacting with oxygen to produce CO2 and water. Or we could have glucose interacting with nitrate, again producing CO2, but now with nitrate as a result in the product. Both reactions can take place. Obviously, the production of nitrite from nitrate doesn't give you as much energy as the production of water from diatomic oxygen, because the drop is bigger in the conversion or the exchange reaction of glucose and oxygen to produce water and CO2 than it is with glucose plus nitrate to result in CO2 and nitrate. We can look at other kinds of aerobic and anaerobic reactions. Aerobicing, or aerobic meaning that those reactions use diatomic oxygen. Anaerobic means that there are other electron acceptors. So one reaction might be, an anaerobic reaction is methane combining with sulfate, resulting in the generation of CO2 and of hydrogen sulfide. Or we could see iron plus 2 interacting with nitrate to form iron plus 3 plus nitrite. Both of those reactions can take place. We see them in the Winogradsky column, but they don't have as much energy being released as the glucose and oxygen to produce water and CO2 reaction. Clicker questions. Which pair of reductants and oxidants would provide more energy for metabolism? CH4 plus sulfate or Fe2 plus nitrate? This is a smaller drop, so more energy would come from A. Secondly, would it be possible for an organism to make a living by using CH4 as a source of electrons while breathing oxygen? The answer, oxygen down here. The answer is, of course, yes. CH4 plus oxygen would result in CO2 and water as products. Clicker question. Which molecule do you think is most likely to be used as an oxidant in the most reductant poor soil? Likely going to be nitrite, because it is reductant poor, and it's ammonia. It's reductant poor, and we don't have oxygen present. The magnitude of the drops, the free energy exchange from glucose to iron, glucose to nitrate, glucose to oxygen, differ. The energy reaction that's going to give you the most energy for ATP is, of course, glucose combining with oxygen. These kinds of reactions become quite important when we begin to think about surface to volume relationships. All of these gases have to move across membranes through the cytoplasm, and in these diffusion-dependent reactions, the surface to volume ratio has a significant influence on the flux rates. You get much higher flux rates in small cells which have a high surface to volume relationship.